prior CPR or infection. We also recorded the person's age, not as young versus old, but the actual age of a person had. 20 years old, 32 years old, 47 years old. And finally, they recorded the blood pressure of the individual at admission. They recorded that, and they also squared the blood pressure, because this is the final model they came up with. The model says, remember, P here is your risk of dying in the hospital. It says, if you look at your risk and divide it by 1 minus the risk. And that should remind people this is nothing more than the odds of dying in the hospital. The model predicts your log odds of dying. It says your log odds of dying in the hospital is equal to minus 1.370, plus 2.4 times whether you are conscious or not, plus 1.8 times whether you're emergent remission or not, plus 1.49 times whether you're a cancer patient or not, plus 0.97 times whether you had CPR or not, plus 0.965 whether you had an infection or not, plus 0.03 times your age measured in years, minus 0.06 times your blood pressure measured in millimeters of mercury, and plus 0.00175 times the square of your blood pressure. Now, the reason I presented this is, why do epidemiologists build models like this? And I think there are two reasons we build regression models in epidemiology. The first, and by far the most common reason, which was probably not the reason that the investigators built the previous model, but in general, the most common reason we build models is to explain associations between risk factors and outcomes. One of the epidemiology textbooks, that's still a great book to read, was written some 30 plus years ago, almost 40 years ago, by Charles Hennekins and Julie Buring. Julie is still here at Harvard with us. Their book was called Epidemiology in Medicine. And it might have been the book that Marjorie Mao used when she took our course at Harvard in the 90s here as a master's student. And basically, Hennekins and Buring make the following point. They say, let's suppose you do a study. You look at the relationship between spam consumption and anxiety. You come up with a risk ratio. But the spam users have lower anxiety risks than the non-spam users. Risk ratio is 0.75, say, for example. Before you can conclude that that 0.75 risk ratio means that spam is protective against becoming anxious, you have to rule out other possible explanations that could be the reason for seeing a risk ratio of 0.75. One of them is you could have a biased study. You could have somehow measured things differently in the spam users, and then maybe spam users are just as anxious as non-spam users. But the way you measured anxiety was different in the two groups, and you've underestimated the amount of anxiety among the spam users. You have a measurement bias. That's one thing we always have to worry about. We're going to be talking about the role of chance for the next 4 weeks. We're going to be talking about p-values and confidence intervals. So maybe that 0.75 is not statistically significant. Maybe the p-value is bigger than 0.05, as it was last week. Maybe the confidence interval contains the null value, 1.0. Meaning, even though the data suggests that spam might be protective, this ratio of 0.75, the data is also consistent and supports the null hypothesis that there's no effect of spam consumption. But now what I want to talk about today, and particularly for the coming weeks, is confounding. Because what we do typically when we build models is we're trying to control for confounding. Now remember what a confounder is from a couple of weeks ago. We want to know that if spam users are more anxious than non-spam users, that's why we're doing this study. And we find that spam users have less anxiety reported among them. But maybe the spam users are mostly women. Maybe the non-spam users are mostly men. And we know women are more mellow. They don't get as anxious as men. Maybe the protective effect we saw among spam users was due to the fact that there was another factor, a confounding factor, namely gender or sex. It was related to the exposure, meaning the spam users were mostly women, and non-spam users were mostly men. It was also a risk factor, a determinant for developing the outcome. Women are less likely to be anxious than men. And it's not part of a causal pathway, meaning what we were thinking about is this diagram, which I think we looked at. Each spam is influencing some outcome. The outcome is being anxious. We want to know whether this top arrow exists. What we're worried about is this other factor, gender, which has two properties. It's related to the exposure, spam consumption. It's also related to the outcome, anxiety. So from this diagram, we notice there are two ways by which spam users can use. It could well be that this top arrow does exist, that spam users less spam use lessens your anxiety. Or it could be that spam users are mostly females. Females are less anxious. And the problem to the epidemiologist is to control for this confounding factor. So how do we control for confounding factors? There are two ways. We can stratify our data set. We can stratify our data set into men only. Another subgroup would be female only. And we could look among the men. We could look at the spam users, compare them to the men who are not spam users. Do an analysis just using men. That analysis can't be confounded by gender or sex. Everybody in that analysis is a male. All the spam users are men, all the non-spam users are men. We do the same analysis now in the women in our data set. Compare the women spam users to the women non-spam users. Again, we have no confounding in that analysis by gender because everyone's a woman. We'll talk about stratification next week, but it's simple. It has some limitations. It's limited to begin with gender. You're either a male or a female, or you have to make continuous confounders into categories. For example, you'd have to take age and break it up into young age, middle age, old age to make similar age subgroups. Because stratification involves putting people into subgroups. As a result, stratification is not very feasible for controlling many confounders. If you want to control for sex and stratify people into two groups, male and female, have two subgroups to analyze. You also want to control for age, and you have three age groups, young, middle, and old, and you further stratify your men into those three age groups, and then your women into those three age groups. You end up with 6 subgroups. You also have to control for hypertension, you're up to 12 subgroups. And the more factors you want to control for simultaneously, the more subgroups you have. But you only have a fixed number of people in your data set. You're trying to spread them over different subgroups. And as a result, each of these subgroups become very small, the number of people in the subgroup. Very imprecise, wide confidence intervals, large p-values. That's the problem with stratification. You just can't do it. You have multiple confounders. So what do? We usually use models. We use regression models, like the one we just looked at. We express our outcome, depth, as a function of the exposures and the confounders. And what this model says, if performed correctly, it will control for both the confounding factors, both categorical and continuous. Because remember, in that previous model, 2 of our factors, age and blood pressure, were not categorized. They were treated on the original scale, the original continuous scale. When we build models, we make assumptions. Those assumptions allow us to potentially control for many potential confounders in a much more efficient way than what stratification can do. But the analysis depends on the appropriateness of those assumptions. I'll say a little bit about that in the coming weeks. But the bottom line is, when we look at our model, look at the coefficient of our exposure of interest, that number is going to reflect the effect of that exposure on the outcome, calling for the other factors in the model. So to see that, let's go back to the mortality prediction model. Let's suppose I was interested in the effect of having cancer on your risk of dying in the hospital. My main focus is going to be on the coefficient, that cancer variable, that 1.49. It turns out that's going to be a measure of how important cancer is for influencing the risk of dying in the hospital. It's going to be a measure of the effect that having cancer has on your risk of dying in the hospital. And to see that, more importantly, it measures the effect of cancer controlling for all these other factors that are in the model. So to see that, let's imagine we look at this model and say, let's suppose we look at a person in the model whose value for consciousness was 0. In other words, he was alert. His value for type, T-Y-P-E, that's a typo here, that should be a T, was also 0. So he was a non-emergent admission. His value for CPR was also 0. He did not have prior CPR. He also didn't have a prior infection. So let's suppose all the values for those 4 risk factors is 0. Let's suppose that person's 50 years old. Let's suppose that person's blood pressure is 140 millimeters of mercury on the systolic scale. That means his squared blood pressure is 19,600 if you multiply 140 times 140. If you plug in these values, In other words, plugging the value of 0 for consciousness, 0 for type, 0 for CPR, 0 for infection, 50 for age, 140 for blood pressure,